the energy extraction phase requires the help of a very important coenzyme called NAD, which stands for nicotinamide adenine dinucleotide. It's a mouthful, so I'm just going to call it NAD. Keep in mind that coenzymes are small organic molecules. They're non-peptide, so they're not made up of amino acids. They're small organic molecules that typically fit into the active site, and they help the enzyme catalyze the reaction. They're not substrates. They're not inhibitors. They're sort of like additions to the protein component of the enzyme. And oftentimes the enzyme couldn't even do its job if it didn't have these coenzymes helping them out. They're partners. There's also cofactors. These are things like zinc or iron or molybdenum or magnesium, small elements that also assist in facilitating the chemical reaction. But we're going to be focusing on the coenzyme NAD. NAD, that D, remember, stands for dinucleotide, which gives you a hint as to what it looks like. It's a dinucleotide. It's two RNA nucleotides that are stuck together. The base on the bottom is A, adenine, and this little guy up here is the nicotinamide. And what's special about NAD is that it's actually oxidizing G3P. It's ripping electrons away from G3P. Remember, oxidation, to oxidize something, means you're stealing electrons from it. Now, whatever gets the electrons, we say that that has been reduced. Whatever is getting the electrons becomes reduced. So NAD+, as it steals electrons from G3P, it becomes reduced. NAD+ becomes reduced into NADH. Whenever you want to know where the electrons are going, just follow the hydrogen. I'll give you a simple example for the combustion of methane. The combustion of methane involves CH4 and oxygen. These are your reactants, and your products are water and carbon dioxide. This isn't balanced, but just stick with me. What's happening here? The carbon in methane is being oxidized, and we know that because hydrogens are leaving it. Hydrogens follow electrons. So if electrons are being stripped away from the carbon in methane and they're going somewhere else, hydrogens are going to follow. So what's being reduced here? Oxygen. Oxygen is being reduced. We know that because electrons follow hydrogen. So as the electrons are stolen from methane, from carbon in the methane molecule, the hydrogens follow it, and you get the formation of water and carbon dioxide. So this is a very simple oxidation reduction reaction. And what's important about this is that energy is going to be released as electrons lose chemical potential energy. The same logic applies here. When we're talking about the coenzyme NAD. So in its oxidized state, when it doesn't have those extra electrons, we call it NAD+, NAD+. But when it steals electrons from G3P, hydrogen's going to follow. And so this NAD turns into, or it becomes reduced into NADH. So the H right here is the H that it picked off of G3P, and electrons follow. High energy electrons follow. And so I think of NAD as like a bucket, right? So NAD plus is like an empty bucket. NADH is when the bucket scoops high energy electrons off of G3P and a hydrogen follows. But we say that it's been reduced because it's gained those electrons. And so what that looks like is something like this. We have an empty bucket, NAD+. Now remember, there's actually a really big enzyme coming in. It's really just the coenzyme NAD+, which is actually facilitating that oxidation reduction reaction. Right? So here's my empty bucket, NAD+. Bucket's going to come in and scoop out some high energy electrons, and G3P is going to lose a hydrogen as well. So you get a hydrogen and 2 high energy electrons, and we'll do like a buzz to represent the high energy level of the electrons. So that's going to happen to both G3P molecules. Both G3P molecules are going to be oxidized. NAD plus comes in, oxidizes G3P. NAD plus is reduced to NADH. Again, these 2 electrons come with it. Buzz, high energy. Now this is a spontaneous reaction. This is a spontaneous reaction, meaning it releases energy. This is important because this little burst of energy that's released, here's a little burst of energy that's released when this redox reaction occurs because it's highly spontaneous. This little burst of energy is actually going to be captured by an enzyme to attach an inorganic phosphate onto G3P. This is super important. Adding another phosphate onto G3P is not a favorable reaction. It is non-spontaneous. So if you want to stick another phosphate onto G3P, you need some sort of energy input to drive that reaction. This is where the energy is coming from. It's coming from the oxidation of G3P. So when G3P loses these high energy electrons, a little pop of energy is released. An enzyme is going to capture that energy and use that to attach an inorganic phosphate onto G3P. Now, what does it mean for the phosphate to be inorganic? It means that the phosphate is not directly coming from ATP. It's just a free-floating phosphate that is not attached to anything. So the phosphate is going to be grabbed onto by the enzyme, and it's going to be stuck onto G3P. Remember, this is not a favorable reaction, so the energy to drive this reaction forward comes from the energy released due to the oxidation of G3P by NAD+. This is really important because now the cell can begin harvesting those phosphates. The cell can begin to extract those phosphates off of G3P and transfer them onto ADP to turn them back into ATP. But it's important because 2 of these phosphates came from ATP, so the cell had to spend 2 ATP, but it's going to get 4 out of it because these phosphates over here on the left that I drew in pink, those didn't come from ATP. So the cell is able to make 4 ATP even though it only spent 2. So you're going to see in a second that there's going to be a net gain of 2 ATP thanks to this process. But I cannot stress this enough. This can only happen if NAD+ oxidizes G3P. That oxidation is providing the fuel to attach the inorganic phosphate in pink onto G3P.